Python offers several ways to remove items from a dictionary. Let's explore 3 essential methods and exactly when to use them. Choosing the right method at the right time is key. Take a look here. We have 3 users, each assigned a unique token. Using the pop method, let's remove the token for user 202. This variable will capture that specific token during removal. Then we can print and view it. Running this code confirms the token is removed and successfully stored. The output from pop is safely stored. As you can see, user 202 is completely gone. But what happens if we look for a user that doesn't exist? Checking for user 203 instead will crash our script. Look at that. Python throws a key error. It tells us user 203 cannot be found. So how do we bypass this crash? Let's see. First, we will safely remove user 202 and print their token. Then, we will attempt to remove them a second time. At this stage, that user no longer exists in our dictionary. This is where the power of pop shines. We can supply a default fallback value. If we examine the official method definition, we see an optional default argument ready to be used. It takes the key, followed by this optional default value. If the key isn't found, it returns the default instead of crashing with an error. By providing this value, we completely prevent any key errors. Running the code now gives us a clean, safe output, token not found. Now, if we target user 203 and execute the code again, it returns no token found while keeping our existing data perfectly intact. Let's test user 203. The pop item method is incredibly useful. It removes the very last entry from your dictionary. Here, we have a debug key set to true. Let's pull that right out. We call pop item on our server configuration variable, which is exactly where our dictionary lives. Notice how we capture it on the left inside a last change variable? This effectively removes the last update made to our server setup. Since we've captured it, we can print it out instantly. Let's see it in action. Check this out. Our last change variable now holds a brand new tuple. The key and value have been cleanly packaged. You can see the standard parentheses right here, confirming it's now a Python tuple. This means you can easily access each individual item by its index position. Index 0 gives us debug, our very first item, and at index 1, we get our value true. Let's rerun this, and there it is, the value true. Look at our configuration now. The dictionary has updated live. The debug key is completely gone. But because we stored it, we can still use it. We extracted it perfectly. But what if you need to secure sensitive data? Imagine having an API secret inside your dictionary. You definitely don't want that exposed. That's where the del keyword comes to the rescue, completely erasing the entry from existence. It's brilliant because the value is never captured or leaked. Yet, it's cleanly purged from your dictionary. Now, you might think, can't we just call pop without saving it? Why prefer the del keyword instead? Because the del keyword signals clear, absolute intent. You are intentionally discarding it. If you just call pop without a variable, other devs might wonder if you forgot to save it. Is it a bug? Del removes all ambiguity. Next up is standard pop, where you pass a specific key that you want targeted and removed. It uniquely allows you to set a fallback default value, just in case the key doesn't exist. If you pass a bad key to the del keyword though, your program instantly crashes. It triggers a nasty key error. But with the pop method, you can pass that safe default value instead. You still don't have to capture the returned data, giving you complete flexibility. It provides the ultimate safety net. So remember, pop item cleanly extracts the very last item, while the del keyword is explicit. It says delete and do not save. Just watch out for those key errors. Do you know the difference between clear and del in Python? Both serve a distinct purpose. Let's break them down with an example. We have a daily cache. This cache tracks our visits, sales, and system errors. When the next day starts, we want to reset everything. We need to keep the variable, but ensure that it's empty. Totally cleared out. For this, we use the clear method. Running this shows the result. When we print the variable, it's still right there, except it's empty. Notice that the underlying class type remains a standard dictionary. That means you can instantly add items. For instance, using an update statement. So for the next day's data, the clear method wipes the elements inside your dictionary, but the dictionary itself remains. The variable still exists. Now, the del keyword is interesting. Using del completely removes the variable name, making it totally inaccessible. Later in your execution, if you try to print it, that variable has vanished. With clear, Python kept the variable alive. so you could still add new data, but del destroys the variable entirely. Let's run this to see the contrast. We hit a name error. This error confirms that the variable no longer exists. Gone. The daily cache is officially undefined. It's gone forever. While clear preserves it for reuse, del destroys it completely. Master this for better Python code. Think you truly master Python if statements? Let's find out. Let's break it down. Teaching Python to a billion people starts with simple steps. Take this temperature variable. It holds the value 31. As a beginner, you might write code like this. Checking if temperature is greater than 30 equals true. If that condition matches, it returns true. Activate the cooling system. But running this actually yields 0 output. Why? Because Python triggers chained comparisons. Here is how Python genuinely interprets this line. It evaluates if temperature is over 30 and if 30 equals true. You might wonder, what on earth is happening? Highly confusing. Remember the golden rule. Read from left to right. First, is the temperature greater than 30? That's true. First condition met. Next, we keep reading from left to right. Now it asks, is 30 equal to true? It isn't. That fails. Not what you expected. To bypass this and fix it, add parentheses right here. Now, we are explicitly checking if temperature is over 30, which evaluates to true. Then, it compares if true equals true. The first part is resolved. You get true on the left-hand side. And on the right-hand side, we have true. Since true equals true, it works flawlessly. But in Python, you don't even need this. You can skip explicit true checks entirely. Simply remove that clutter and write, if temperature is over 30. Other languages require bulky syntax or conditional logic. In Python, a clean colon at the end is all you need. No need to explicitly verify truth. Python evaluates it implicitly. The statement naturally returns true. If true, the code block runs. Now, let's step up the game. How does this apply to evaluating a range like age? Let's read it together. Apply the rule. Read from left to right. Is 18 less than or equal to 25? Yes, it is. That initial comparison evaluates to true. Next, is 25 less than or equal to 65 also true? Both individual parts evaluate to true. Combined, they confirm this is a valid working age. Run the script and it prints working age. But what happens if we reduce the age value down to 10? We get no output. Python asks, is 18 less than or equal to 10? Absolutely false. 18 is greater, not less. The second part asks, is 10 less than 65? That's true. But false combined with true means the overall condition fails. It lacks a matching truth. Execution stops. This reveals Python's under-the-hood magic. It evaluates 18 less than age, injecting an implicit AND condition, checking if age is also under 65. You do not need any parentheses here. Adding them completely breaks the logic and corrupts your output. It forces a Boolean comparison that alters the entire evaluation, leading to unexpected errors. Parentheses force Python to evaluate Booleans as numeric values internally, where false corresponds to 0 and true corresponds to 1. That ruins your final output, so keep an eye out. While if statements look incredibly basic on the surface, hidden traps like comparison chaining can completely derail your code. Replay this video to master this Python superpower. Here is how you use else if in Python. Python evaluates these conditions from top to bottom. It checks the very first condition and then moves straight to the next one by one. But the moment it finds a match, take a look. Our response time is less than or equal to 15, which evaluates to true. Since the first condition failed, this block triggers. The code executes, prints our target output, and instantly skips every single remaining statement. That is pure efficiency. Instead of stacking multiple clunky if statements to check if the response is less than 5 over and over, avoid that trap. Deploy else if instead. It creates an elegant short circuit, meaning your program bypasses unnecessary code entirely. The moment a criteria is met, Python discards the rest. Let's run this. We get high priority because our value is 12. Now, what happens if we change this to 29? Python is forced to evaluate the first line first. Remember our rule, top to bottom. Next, it checks the second line, and then it hits the third condition, which successfully matches. As a result, it completely ignores the final block. Let's push it even further and go above 31. Boom! Now we see low priority flash on the output screen. The final condition executed, but only after checking every single option above it. It had to process the entire chain before reaching this point. Mastering ternary logic is a game changer for your Python workflow. What is this line of code is doing? Let's break it down so you can master it instantly. I love making complex code feel incredibly simple. By the end of this, you'll see why ternary syntax is the secret to writing cleaner, more professional grade code. Look at this variable called latency. It's currently set to 120. Our goal is to update the status variable to healthy if the latency is under 200. Otherwise, we want to show that the connection is slow. The status would become slow. This if statement right here is the full-length version. This is the old school way to do it without ternary syntax. But with ternary syntax, notice the sleek efficiency. It does this in a single line. The logic flows straight through. If the condition is true, this first value is assigned to the variable. If not, the second value takes over immediately. Contrast that with the standard if statement logic. You'd write, if latency is under 200, status equals healthy. Notice all the extra colons and spacing. If I highlight this, you'll see the repetitive nature. You have to type the word status twice. First, for the healthy state, and again for the else part if the connection is slow. It's a lot of manual work. All those colons add up. Ternary gives you a compact, elegant syntax, handling the assignment on just one side. It reads, healthy if latency is under 200, else slow, no colons, no repeating the variable name. It just looks and feels better. It's much more readable. When you read this, the logic is clear. If the condition holds, use this value. Otherwise, use that one. I prefer this style because it's modern and marks you as a professional. This simple change puts you in a higher league than those stuck writing code the old-fashioned way. Look at the difference. That's the legacy style, and you don't want to be writing legacy code. You want your Python to be sleek, modern, and ahead of the curve. Ever wondered what Truthy and Falsy values are in Python? Let's explore a practical example to make it crystal clear. Check out this scenario. An API response. If the request fails, we might get a blank result, or no data at all, and a blank response is sent through. When you handle that with an if condition, like if API response, it should print data received. Otherwise, it says no data is available. In this case, the API response variable is currently empty. In Python, an empty value like this defaults to false. Therefore, the code will skip the first block and execute this else block instead. However, if it is populated, the condition becomes true. Let me show that for you. I will add a value, the word test, so we can see the change. Running this now, you can see the output is data received. But if I leave it completely blank, we get no data available. Notice this. If I leave empty quotes inside a container, the system assumes data is received as it isn't truly empty. The container itself is the data. Even an empty string is a type of content. But if I delete everything, we go back to no data available. To master logic, you must recognize these false e values. False e values are the specific cases that evaluate to false. This includes 0 and a standard empty string. But keep this in mind, there's a big difference between an empty string and a collection that contains an empty string. Here, we have a set as the container, and inside it is an empty string. Now, if I use just a plain empty string by itself, you will see that no data is available. But watch what happens as soon as I wrap it in a list. Check out how the response changes. It flips to data received as the list itself is not empty. This applies to empty sets, dictionaries, or the none type. None and false are also inherently false e. Everything else is truthy. For example, if I add a single dot, that counts as data received. It's content. If I add a single space, it is still data received. It is no longer empty. It is a truth e value in that context, but if it is totally empty like this, it is false e. If any of this is unclear, please comment below, and I will be happy to explain it further. I hope this clarifies the trickier parts of the logic, specifically empty strings versus data inside other types. Hopefully, this has made the concept easy for you to grasp. If not, just let me know and we will dive deeper. Ever wondered what the pass keyword does in Python? Pens down, eyes up. This is a coding essential you will remember forever. Let's master this fundamental concept. We have a variable here called feature-enabled set to true. If that condition is met, I want to execute code inside this block. But right now, I'm not ready to write that logic yet. I need to save this spot for the future. When you need a gap in your logic, use the pass keyword. It acts as the perfect placeholder for code you will finish later. It keeps your script running smoothly. See, look at this print statement. It isn't actually part of if block. It is an independent line of code. The block only triggers if the condition is true. Running the script now, system is running appears. This executes regardless of our true or false status. If I switch to false, the system still runs perfectly. No problem at all. Let's flip it back to true and run it again. The system is active, even without logic inside the block. But watch what happens when I add real code. I will add a new print statement here, labeled test. Now the feature is implemented. Great, I can finally remove the pass keyword. Running it now, we get both test and our system output. But if I toggle the feature to false, the test output vanishes, just as we expected. The system line stays because indentation defines the logic block. Only the indented parts are part of that if statement. Clear. The rest is standard execution. It always runs, switching back to true now. But let's look closer at pass. Why is it mandatory? Suppose you define an if statement, but are not ready to code it. You cannot leave it empty. Your program will crash. See that? An error occurs. Python explicitly requires an indented block here. Without content, the script breaks on line 3. Watch, this is vital. The interpreter expects a statement to follow that colon. To fix those red errors, simply insert the keyword pass. Immediately, the error vanishes. Let's run the code again. System is running. Success. The pass keyword is your ultimate coding placeholder. Simple as that. It is a lifesaver. Use it to keep your momentum while you build the rest of your app. The match statement arrived in Python 3.10. It functions just like the switch statement. You've likely seen in other languages. It's elegant, fast, and incredibly powerful. But first, let's look at the old way. Before we had match, we relied on long chains of logic to handle variables. If you had an action variable like delete, you had to check every single possibility. Is the action create? Is it update? Or is it delete? Otherwise unknown. It works, but the syntax starts to feel very repetitive. You find yourself writing if and else statements over and over again. It's a lot of redundant code that clutters your script. See how action is repeated everywhere. Equal to create, equal to update. It's tedious, but with the match statement, we can streamline this entire process. Simply match against the action variable and use a colon to start your block. While if statements still have their place, the match syntax is far more readable. Use match action, a colon, and then define your first case, create. Add another colon and specify the code you want to run. You can include multiple lines of logic inside each case. The key is to keep your indentation consistent and clean. We can define cases for update and delete, but what if the input doesn't match? That is where the underscore symbol comes into play. The underscore acts as a catch-all, matching anything that wasn't caught above. It's your ultimate fallback whenever the criteria aren't met. Think of it as the else block for your match statement. Notice the clean structure, a colon for every line and the case keyword for every option. It keeps your code organized and easy to maintain. When we run this, delete is selected, so deleting prints to the console instantly. It achieves the same result as the if statement, but with much better clarity. The logic flows straight to the correct case and executes the code. This is start of what's possible. Match statements have so much more to offer. I'm going to show you. Hit like and subscribe to join the community. I'm on a mission to teach 1 billion people Python. I want you to be one of them. Let's keep coding.